Bismillahirrahmanirrahim. Aziz Talba, Assalamu alaikum. We are studying nuclear stability and instability. In our last discussion, we studied about the nuclear science and the parameter that actually affect the stability of the nucleus. First of all, we just go through about the nuclear science, and then we will study the basic parameter that affect the stability and instability of the nucleus. So, what is meant by nuclear science? There is a change inside the nucleus of an atom. Study of such type of changes and then consequences is called nuclear science. Okay, these changes are of two kinds. One is spontaneous that occur itself, but other is programmed that is created through a systematic program by the bombardment of some particles over the target material in order to activate or disintegrate into subatomic particles. So in this regard, programmed fission or programmed activation process associated with a lot of application in our daily lives, as we studied, as quoted here: power sector, agriculture, medical, environment, other sectors of life like that, petrochemicals, petroleum industries. So nuclear science play a very crucial role in our daily life. So it is very important to study different parameters that actually associated with the nuclear science. First of all, what is the nuclear stability? Up till now, there are 118 elements we have placed in periodic table. Out of these 118 elements, 94 elements are those which are naturally occurring. And out of these 94 naturally occurring elements, there are 6 elements that occur in very trace quantity, like the technetium, promethium, astatine, francium, neptunium, plutonium. So these all atoms or elements are in very trace quantity, but the rest of the and 88 elements that which are actually naturally occurring exist in heavy quantity and make the main earth crust. Other 24 elements are artificially prepared. That is actually the consequences of the nuclear changes by through programmed process, that may be fission process or through the fusion process. So all these elements, consist of basic part that are called atom, and atom have two main part. One is orbital and other is a nucleus. Orbital are of having electron having the negative charge over them, but a nucleus having main two kinds of nucleons that are called proton and neutron. There is positive charge over the proton, but there is no charge over the neutron. So atoms of same element may exist in different formation set of proton and neutron number. However, the number of proton remains same in atom of an element. Yes, it is very important point. One element have a not only similar kind of atom. Atom are similar with respect to the proton number, but they are differ with each other according to their proton and neutron number. So there may be 2, 3, 4, 5 different set of different neutron number inside the uh, atoms of an element. Due to this, like that, you can see here, hydrogen atom have 3 different atoms, hydrogen elements 3 different exist in 3 different atoms, like that, hydrogen 1, hydrogen 2, hydrogen 3. Hydrogen 1 means there is only one proton in the nucleus of an atom of hydrogen, and here are one proton and one neutron, and in tritium there is one proton and two neutron. So these are the 3 atoms of hydrogen element. These 3 atoms are differ with each other through this proton and neutron number. So such type of element, such type of atoms of an element are known as isotopes of an element. Other example of such kinds is uranium. These are the basic and most abundantly available and used isotopes of uranium. In it, if we see here, there is 92 protons which are specific for uranium, but in different atoms of uranium, the number of neutrons are also different. So here are 142 neutrons, and here are 143 neutrons, here are 146 neutrons. So in other words, you can say that the mass of all atoms differ with each other. So these are also an isotopes of uranium atom. Collectively, all these different set of proton and neutron inside the nucleus are known as nuclides. So what this means by nuclear? A distinct kind of atom or nucleus characterized by a specific number of proton and neutron. So such nucleuses are called nuclides. Such atoms are called nuclides. So up till now about 3000 nuclide was discovered. Out of these 800 nuclides are highly reported, mean which have a sufficient half-life to study them and to report. And out of these 800 are 3000 nuclides, there are 274 nuclides are highly stable. So it means that at least more than one nucleus is one nuclide, yeah, one formation for proton and neutron for an element is stable, but it is not necessary more than one nucleide may also be stable for one element, as reflected from this number. As there are only 118 elements so far present in periodic table, but we have 274 nuclide that are stable. So it means there are more than double uh, a number which actually is stable. So one proton and neutron formation for each element is stable, and rest of them may or may not be stable. So it is possibilities that more than one nuclide for an element may be stable. So what is mean by stable? Undergo no nuclear change. Unstable mean undergo nuclear change. Nuclear changes may be of two kinds. One is a spontaneous change as we have studied earlier, and other is a programmed instability. So programmed instability, that is a programmed nucleus changes, can be created through two main processes. One is a cyclotron process and other is a atomic reactor process. Through cyclotron process, the process is just an activation of an element, atom or nuclide. So such nuclides are actually small nuclides most probably. And in case of atomic reactor, the target material most probably are used with a heavy nucleus like that uranium. Here also activation process proceeded as there is an analytical technique known as a neutron activation process. So neutron are used for both processes, even fission process as well as for activation process. So it gives you a lot of information, particularly in activation process. In analytical technique, nuclear analytical technique play an important role in order to study different kind of matter in all industries as well as in different analytical samples. But in case of fission process, it in its own place play a very important role. Like that uranium when bombarded with the neutron inside the atomic reactor, it produces a large number of different kinds of daughter nuclides with a big amount of energy that is utilized for the production of electricity. So such type of daughter nuclide further uh, proceeded through the rearrangement process, and due to this rearrangement process they emit they liberate different kinds of radiations like that beta radiation, positron radiations, and alpha particles, gamma radiation. So all these radiation are utilized in different sectors of life, particularly in agriculture, environment, and for the medical field. So these unstable nuclides stabilize themselves to adopt nearest stable formation of proton and neutron. So it should be in our mind about the stability that there is a particular formation and there is a particular number of proton and neutron which for an element um, present inside the nucleus to stabilize the nucleus. If the proton and neutron number is disturbed, which is associated with stability of the nuclide, the nuclide no more longer will be stable. So in this regard, in order to adopt such formation, because there are certain different kinds of formations for uranium atom, hydrogen atom, and like that all the atom element present inside the periodic table, all these elements in the periodic table have such type of nucleides having different set of proton and neutron. But all these uh, out of all these, only one or two nucleides may be stable, rest of the nucleides are not stable. So what actually other unstable nuclei do, they undergo nuclear change in order to adopt the stable nuclear formation. So here is, so in order to achieve such a nuclear formation of proton and neutron, they undergo decay process. There are certain decay processes we have studied. We have discussed beta decay, positron decay, alpha decay, electron capturing decay, or asymptotic transition. So other thing that we studied is the KY decay process proceeded. This is a very simple process, that is in order to decay process proceeded in order to adopt the proton and neutron number. So what happened? What type of forces actually exist inside the nucleus in order to adopt such formation? There are two main kinds of forces inside the nucleus and in the atom. One is Coulombic force and another is a strong nuclear force. Coulombic force actually exists between proton and outer orbitals as well as inside the nucleus. But in strong nuclear forces only exist between in the nucleus, between proton, between neutron. So these are the strong nuclear forces. These are the two forces out of four naturally existed forces, like that the two was gravitational force and weak nuclear forces. So Coulombic forces may be repulsive forces, may be attractive forces, depending on the charge particle. If there are opposite charge particle, then it will be attractive forces. If these are similar charge particle, it may be repulsive forces. So this force, that is a Coulombic force between electron and proton, actually hold the atom together. Otherwise, if there is a repulsive force, so no more longer proton and nucleus and the orbitals will exist together inside the nucleus. So this is a Coulombic force that actually bind the outer orbital and inner nucleus, two parts of the atom together in an atom with no charge. Inside the nucleus, this force operated between proton only, but inside nucleus it is not operated between neutron and neutron, between neutron or proton. So its strength is weaker as compared to the strong nuclear forces, due to which in a nucleus strong nuclear force dominates. However, this domination not in all cases in all formation of neutron and protons, but in that case in which the proton and neutron reflect the stable configuration inside the nucleus. As there is a specific ratio between proton and neutron inside the nucleus which impart stability to the nucleus. If this ratio is disturbed, this nucleus no more longer will be stable. So other is a strong nuclear force that exists among the nucleons of a nuclei. This force operated between neutron, proton. However, it dominates over Coulombic repulsive force among protons. It must be, else the nucleus would fly apart. Why nucleus would fly apart? Only in case when there is the specific ratio between proton and neutron is not exist inside the nucleus, then such type of force is not in equilibrium, and due to this reason nucleus have feeling instability and at any time decay into stable formation. So when this situation appears, when nucleus may fly apart, may decay, may disintegrate, This is the situation when nuclear forces fail to overcome the Coulombic repulsion, and it appears when the number of neutrons associated with proton number for particular element in stable configuration is not like that. It is less or more. So in such cases, there is instability exists inside the nucleus that actually apart some uh, nuclear changes to the nucleus, and due to this reason new formation of neutron and proton number inside the nucleus created, and due for to adopt the nearest possible nuclei formation which is stable. So star nuclear forces are short-range forces and operated in a small distance. And that distance is just like about 10 raised per minus 15 meter. So this is also known as femtometer. 10 raised per minus 15 meter is exactly is equal to femtometer. So in some reports it is represented that these short-range forces, the forces, strong nuclear forces that exist between the nucleus, there are about zero point 0.5 into 10 raised by minus 15 meter to zero point 0.7 into 10 raised by minus 15 meter, or in some cases it is uh, like that zero point 0.2 into 10 raised by minus 15 meter to zero point 0.7 into 10 raised by minus 15 meter. So this is a range of strong nuclear forces that operated inside the nucleus. We come to the point now how these forces operated inside the nucleus and how these nuclear forces, strong nuclear forces, overcome the repulsive forces. If have a look at this graph, please. So come from moving from this point. At this point, the two particles, proton and nucleus, are which is approaches to this nucleus at far apart from each other at a maximum r distance. So when moving from here to this point, they come close to each other. As they come close to each other, the repulsion between these 2 point charges due to Coulombic repulsive forces increases. And at this point, the two particles are approaches to each other in such a way and so close to each other, the strong repulsion forces appear to be at its highest point. So beyond this point, when further they come close to each other, what actually happening, and the distance further decreasing the distance between these 2 points, the strong nuclear force is going to operate, because now the distance between these two nucleons, between these two particles, now in the limit of 10 raised to minus 15 meter. So in this regard, further uh, and closing of these two particles between each other, the strong nuclear forces further increases, and at this point, the potential energy of the system rapidly going down, and this is the point when strong repulsive forces bind all the nucleons of the nucleus in a stable nucleus. But this is the point at which the repulsive forces and strong nuclear forces get equilibrium with each other. So this is just equilibrium when these two forces appear to equal each other or just nullify to each other. But beyond this distance, if this distance further decrease, so due to this reason, what actually happening? Further strong nuclear forces appear between the nucleons, and potential energy going down, and how huge amount of energy is liberated by the system, which actually guarantee the stability of the nucleus. This is the case of proton, but if there is a neutron in place of this particle, like that, if we see here, there is no charge over there because neutron have no charge. So in case in place of proton, this is a neutron. So when this particle approaches to the nucleus, so it felt nothing like that Coulombic repulsive force because it is a chargeless particle. So there is no increase in potential energy. There is no increase in energy inside the system because there is it is not feeling any type of repulsion from this point charge nucleus. So case is that when the nucleus a proneutron approaches to the proton or nucleus, so there is no increase in potential energy, just they come close to each other, and when reaches at the point of strong nuclear forces and further come close to each other strong, the potential energy of the system suddenly decreases, and the system of the nucleus appear much more stable. So when the neutron reaches the strong nuclear force limit, the strong nuclear force operation allows the system potential energy to make it sufficiently stable by liberating huge amount of energy. However, this amount of energy that liberated by accepting a neutron by a nucleus is much greater as compared to the energy liberated by the proton, when proton enter into the nucleus. Why this is we will explain in next slide. So equilibrium point appears for stable nuclide. However, for unstable, this point not appear before decaying process to stabilize to get the formation of a proton and neutron number, which give the stability to the nucleus. So the Coulombic repulsive forces and strong nuclear forces inside the nucleus and the achievement of equilibrium point we can study and explain with another way by using separate graphs of these two forces. If we see here, there is a Coulombic repulsive force graph here. When a positive charge approaches to other positive charge, what actually happen, the distance going to decrease, these strong repulsive forces increases. But in case of the strong nuclear forces, what actually going to happen when these 2 point charges come close to each other, the strong nuclear force is going to increase operating between these two nucleons. So at this point when these two nucleons come close to each other at a maximum distance at which the strong nuclear forces operate heavily, this potential energy of the system going to decrease very rapidly. But beyond this distance, when these two nucleons approaches to each other further, the repulsive force is going to increase, and no more attractive forces like their strong nuclear forces exist there, and the system going to unstable by increasing the potential energy of the system. So these two graphs could be explained in one graph as we have studied in previously in like the in this graph. So initially the when the charge particle come close to each other, the repulsive force is going to increase, Coulombic repulsive force is going to increase, but after that uh, when the distance reaches between the nucleons, which actually the, the operational distance between two nuclei for strong nuclear forces, the strong nuclear force is going to increase, which initially overcome the strong Coulombic forces, but then going to decrease the potential energy of the system to stabilize the system in good way. So, however, but later on, as I have discussed here, when these nucleon approaches further to each other, uh, then these beyond the limit of the strong nuclear force distance, this force quickly die, and repulsive force again start to increase, which actually unstabilize the system, and nucleus may undergo some nuclear changes. So these two forces at some point appear to as an equilibrium point. So we can see here, this is the point when the Coulombic force is going to increase by decreasing the distance between 2 point charges. When this distance going to decrease, the repulsion going to increase very rapidly. But on the other way, when this distance decreases between these two particle nuclei inside the nucleus, the strong nuclear force is going to operate. And at this distance, okay, at this distance, this distance, what actually happened, the strong nuclear forces operate between these two particles or nucleons. However, when these two particles come further close to each other, that is beyond the limit of strong nuclear forces, the repulsion forces also going to increase. So at this point, there is some uh, balancing point between at which the Coulombic force and strong nuclear forces become in equilibrium, and this is that distance at which both forces appear to equal. But if this distance further decreases, what actually happens? This force is of like that Coulombic repulsion force is dominated by the strong nuclear forces, and it appears as a highly is less potential energy of the system, which actually stabilize the system, guarantee of this system stabilization. So there are not only proton inside the nucleus, but there are other particles also there, like that neutron, and also some binding forces, strong nuclear forces exist between neutron and neutron, proton and proton, and neutron and proton. So what kind of potential energy actually decreases, and what kind of strong nuclear forces operated between other nucleons, we can see in this graph. Okay, so if we see here, there is a force of attraction in an atom between electron and proton, that is not inside the nucleus, but it is between nucleus and the outer orbital electron. So this force of attraction is very small, because in due to this force of attraction, that is Coulombic force of attraction, so very minute and decrease in potential energy actually appear. Okay, this is potential energy, system potential energy decrease, like that up to here. But if we see about the proton-proton interaction, so this is like here. Okay, so this is up to here. But if we see this is a strong binding force between proton and proton inside the nucleus, strong nuclear binding force. So if we come to this point, proton and neutron, so here if we see the potential energy going to decrease up to this point. So this potential energy going to decrease greater as compared to other two forces, but in case of a neutron and neutron interaction, the potential energy decrease is very much greater as compared to other all type of interactions. Okay, so what actually happening is here, and why the neutron-neutron interaction is so much stabilized as compared to other, because if we see here, there is only Coulombic force. Here is two type of forces exist between proton and proton. Proton-proton, there is a Coulombic repulsive forces, there is a strong nuclear binding forces. So first of all, nuclear forces also have to overcome the strong Coulombic forces. Then other uh, force, strong nuclear force appear to stabilize the nucleus and decrease the potential energy. But in case of this system, it is although it is greater, uh, provide the stability to the nucleus as compared to the proton-proton interaction. But this thing is that proton also involved in some other proton in repulsive forces, and in other way it is involved in a strong nuclear force. So there are also two type of factors are here. Due to this factor, this proton, it is which is involved in its neighboring proton in its repulsive forces. Due to this reason, it also have to overcome that parameter, that force of repulsion. So due to this reason, it is somewhat at higher level as compared to neutron-neutron. But in case of neutron-neutron, this neutron and this neutron, which are involved in binding energy between each other, but these none of them is involved in any type of Coulombic repulsive forces. Due to this reason, total binding energy utilized in order to decrease the potential energy of the system. Due to this reason, the system is highly stable. So these are different factors which actually involve in the stability of the nucleus and in instability of the nucleus. Inshallah, in next lecture we will study about what type of decay process actually operated inside the nucleus in order to stabilize the nucleus, in order to acquire the equilibrium and decrease the potential energy to appear as a stable nuclei. Dear students, Assalam.